Good morning, student. See, welcome to Urban Pro. In this session, I am going to discuss photoelectric effect. Due to this photoelectric effect, Sir Einstein got Nobel Prize. So definitely, this photoelectric effect must have brought some revolution in science these days, isn't it? That is why Einstein got Nobel Prize. So what this effect is actually? Photoelectric effect. As the name suggests, photo, if we break it into photo and electric, photo means, as you know, it is light. It is all about light. And electric means somehow, somewhere electric means we'll understand something like flow of charge. Flow of charge. Okay. So now let us discuss what is this photoelectric effect. Okay, see, suppose this is a metal surface. This is a metal plate. Okay, let us write here. This is metal plate. Okay, now light will incident on it. Light will incident on it. Suppose, so far as we know, light is an electromagnetic wave. It has some frequency f. It is incident on metal plate. So when light or electromagnetic radiation is incident on metal plate, sometimes electron emits from metal surface. I repeat, sometimes electron metal surface out of metal surface when radiation, electromagnetic radiation or light is incident on metal surface. Okay, this is photoelectric effect. Photo means light is incident and charge is emitting from the metal surface. Now we will analyze what happens inside it. Okay, so as I told you that sometimes, not every time, that is, light is incident of any frequency and electron is emitting. This is not the case. Sometimes it means there is some frequencies for which electron emits from a particular material, metal plate, and there are some frequencies for which no electron emits from the metal plate. Okay, what we see is actually, suppose for this metal plate, for this particular metal plate, this is a electromagnetic wave of frequency f0. For example, let f0 is equals to 500 hertz. It is its frequency. Okay, when 500 hertz frequency, electromagnetic wave of frequency 500 hertz is incident, electron is start to emit. Now if frequency greater than 500, that is, suppose frequency is 501 hertz is incident, then also electron will emit out of this metal plate. Greater than frequency greater than 500 hertz will cause the emission of electron from the metal surface, but less than 500 frequency will not emit electron from the metal plate. That is, for this electron will emit, for this 501 electron will emit. But now if I take one more wave of frequency, suppose 498 hertz, this will not emit electron from the metal surface. Okay, so what do we see here? We see there is a certain frequency for which electrons start to emit, and if the frequency is more than that, electron will emit, but less than the certain frequency, no electron will be emitted. This particular frequency for which the electron emission take place, start to emit, this frequency is known as threshold frequency. So we will write the definition of threshold frequency. The definition of threshold frequency. What it says, it is the minimum frequency, the minimum frequency of electromagnetic radiation for which electron emits from metal surface. This is called threshold frequency. Okay, now we will discuss, see the image, or the for the time being we can analyze this. That's yes, electron emits to emit an electron from the metal surface. Definitely there is requirement of energy. Electron can't emit without any external energy. Electron needs some energy to get out of this metal surface. Probably here the energy is supplied by the electromagnetic radiation or light wave. But then why there is a certain frequency, if not threshold frequency, why the frequencies less than the threshold frequency are not able to emit the electron out of the metal surface? The reason is, we can't, first of all, we can't explain this using wave property of light or electromagnetic radiation. As we know from our earlier chapter, light has two properties. One, particle, another, wave. Light has dual nature, particle and wave. In this case, the particle show the wave, the light shows particle nature. We will discuss the particle nature of light. What is that actually? See, as we had the metal surface, this is the metal surface, and the light wave incident on it. Suppose its frequency is f. Suppose its frequency is f, or f. Then we consider the light here is, a light consists of discrete wave packets, that is photons. So light is traveling, that is nothing but the flow of some discrete energy packet, and we call this as photon. Okay, so what is this? This is photons. And how we define photon? Photon is nothing but the discrete energy packet, discrete energy packet. Okay, so it is a packet of energy that flows. Okay, so now, as you know, lots of electrons are there inside the metal surface, and they require some energy to get out of this metal surface. Now what happens is, the photons collide with this electron, and simultaneously, that is, there is no time gap, immediately electron get out of this metal surface, if and only if they get the minimum energy required by them. Suppose a electron, I am talking about this electron, it requires some energy. We call this as work function. It requires W naught amount of energy to get out of this metal surface. If this W naught amount of energy is supplied by these photons, by only one photon, then the electron will be emitted. If the W naught amount of energy is not being supplied by a photon, then electron will not be emitted. If the energy supplied by the photon is more than the required minimum required energy, that is W naught, then definitely the electron will be emitted, and the emitted electron will have some kinetic energy. Okay, so here first of all we will define work function. What is work function? It is the minimum energy required by an from electron to emit from metal surface. Okay, it depends on the metal only. That minimum energy, depends on it depends on material of metal. Okay, so now from the conservation of energy we can write, see one more thing. What is the energy of each photon? Suppose it is the photons of a electromagnetic wave whose frequency is f, then the energy of each photon is hf. Okay, now suppose hf, I am talking about hf naught, that is now the frequency, the threshold frequency, electromagnetic radiation of threshold frequency is being incident on the metal surface, then electron will just emit. So let me write, suppose H F naught. F naught is the threshold frequency. What is the energy corresponding to a photon? Hf naught. Okay, this will be used to emit an electron. That is work function W naught. That is totally used. So there will be no kinetic energy of electron. Now suppose the incident frequency, the frequency of the incident wave electromagnetic radiation is greater than the minimum frequency, that is threshold frequency. What will happen in this case? In this case, the energy incident is what? Hf, isn't it? And a part of this Hf will be utilized to just to emit the electron out of this metal surface, and rest of the energy will be visible as the kinetic energy of the electron. We will say kinetic energy maximum. Why? The reason is we are writing here W naught, that is the minimum energy required to emit electron. To emit all the electrons, for the emission of all the electrons, W naught energy is not used. It is the minimum energy used. More than W naught energy is used for other electrons. In that case, definitely the kinetic energy will not be maximum. Kinetic energy will be maximum for those electrons which has been emitted by consuming or by absorbing W naught, that is minimum energy. So we write Hf is equals to W naught plus kinetic energy max. So this equation is known as Einstein equation. Okay, we can write it by multiple way. How we can see this work function can be written as Hf naught as well. So Hf is equals to Hf naught plus we can write kinetic energy max. This one is also Einstein equation. We can write it as Hf is equals to Hf naught kinetic energy max. We can write half m v max square. This way also we can write. See, from this we can plot some graph as well. What are the graphs? Suppose we want to plot some graphs like in xy and y axis. What we will plot along x axis? We will plot, suppose, frequency f. We want to plot frequency f, and in the y axis we want to plot, suppose, maximum energy Emax. Okay, as we know, the photoelectric emission will be started from a certain frequency f naught, threshold frequency. Before that, when the frequency is less than the threshold frequency, no electron emission will take place, isn't it? So along y-axis we are plotting kinetic energy maximum, and okay, so consider this equation number 2. Okay, we are using this now, and from this we can write what? Emax is equals to hf minus h f naught. Correct. As I am plotting f in this here along x-axis, so how it will look like? See, y is equals to mx minus naught plus c. So it is a straight line, so it will be a straight line. The graph will be a straight line. See, mx plus c, so m is here, this h. So the slope of this graph is equals to h is equals to Planck constant. Slope is Planck constant. And as the slope is constant, so for every curve, I mean, suppose this is material A. Now, if we want to plot the same graph for material B, it will look like same straight line whose slope will be again h. Suppose this is material B. Suppose this is material C. Its slope will also be h, that is Planck constant. But for all the cases, the threshold frequency is different. The threshold frequency is different. I write f naught b, for this f naught c, for this f naught h, f naught a. Okay, so threshold frequencies are different for different material. As we see, how do you know threshold frequency is different for different material? See, it is related to work function by this equation. So f naught is equals to work function by h. H is constant and work function depends on the material, so yes, threshold frequency depends on the material only. Okay, but the slope of for every graph will be same. Now if we want to extend the graph, then we can extend it by dotted line, not solid line. The reason is there is actually the photoelectric emission is not taking place, is not taking place, isn't it? Because these frequencies are less than the threshold frequency, so actually there will be no emission of electron. But we can find out what will be the intersection with the y-axis. What will be that? It will be, see, when the frequency is zero, when the frequency is zero, Emax is equals to hf naught, isn't it? Okay, using some mathematics you can do it. We'll proceed into the further discussion. See, this photoelectric emission, how we discovered it, how Einstein discovered it. See the experiment. Suppose this is a tube, okay, and here there is a path through which light can enter. Okay, through this light can enter. Okay, and here a light will enter how? Suppose that's how light will enter. Okay, and here we will place a metal surface. We will place a metal surface. So light will incident on the metal surface like this. And we will definitely now complete the experimental setup. Here one more plate is placed and a battery source is connected like this. I am saying one by one. These are the connecting wires. Okay. So see, when light enters, light is entering. So electron will be emitted. Suppose this frequency is greater than the F naught threshold frequency, light will emit and they will after emission they will move in every possible direction, isn't it? They will be scattered in here and there. They will not be oriented towards this plate. They will be scattered here and there. Then some of the electron will be able to reach this plate. Now suppose here I will add a power supply. The power supply has to actually attract this electron, that is the positive side will be there, negative side will be there. But when the potential is zero, when the potential, let me draw the curve. In this direction we are plotting this F and in this direction we are plotting current. When the potential is zero, only few electrons comes and touch this plate and current flows. So we actually get some electric current even when the potential is zero. When we increase this potential, the current will increase. Why? Initially, when there was no attracting force on the electrons, still few electrons come and incident on the metal plate and flows through this wire. But when increase this power supply, actually we increase the electric field inside the tube and the electrons gets attracted by the metal plate, this plate, and actually they gets oriented towards the surface, this plate, and they touch the metal plate and they flow through the battery or the ammeter here. That is why the current changes, increases, and finally the currents get saturated. Why? Yes, it is true that suppose I consider here a cross section area. When I increase the electric field inside the tube, the electrons gets oriented towards the orientation of the electron towards the plate increases, but a certain time comes after which even if I change the electric field inside the tube, the number of electrons inside the tube is fixed. That is decided by this what? Incident light. How much photons are incident on the metal plate? Suppose in 1 second 100 photons are incident on the metal surface, then definitely 100 electrons will be emitted or less than that. If I increase the electric field, definitely not more than 100 electrons will emit from the metal surface, isn't it? So there is a limitation on the intensity of the light, incident light or electromagnetic radiation. That is why we get the saturation current. Fine. Now let us just, we need some one more setup, and here we can easily set it up here to explain the other part. See, here what we will do, we will just change the polarity of the power supply. Why? See, when we apply zero potential, then also we find some current. Now we want to stop the current. For that, definitely we have to apply the electric field or the voltage in opposite direction. We are going to do so. We are going to apply negative potential or potential in opposite direction. We will keep increasing the potential in negative direction. That is, we will move on. We will move on to we will increase the potential but in negative direction, and we will check what happens for current. What happens is actually the current decreases. Yes, the current should decrease. The current should decrease when there is no potential. Some electrons come able to reach this plate, but now we are opposing, so less electron will be able to hit this plate, so the current will decrease. This is obvious. We keep changes, we keep on decreasing it or increasing in the opposite direction. What happens? The current comes to an zero like this, and we call this particular potential as stopping potential. So it is that negative potential for which the photoelectric effect or photo emission of the photoelectric current becomes zero. The photoelectric current becomes zero. Okay, so Vs is the stopping potential. On which factor does this photo stopping potential depend? Here we are applying some negative potential, opposing potential to stop the electron. To stop which electron? We are stopping that electron which has the maximum kinetic energy. If we stop the maximum kinetic wala energy to touch this metal surface, then definitely all the electrons having less energy will not be able to touch this metal surface. So what we are doing here, we are somehow opposing the electron of with maximum kinetic energy to touch the metal surface. How much energy we require for that? At least we have to apply energy which is equals to the energy of that electron which is maximum kinetic energy. But we are applying here potential. Suppose we are applying stopping potential is Vs. What is the corresponding energy? EVs. EVs is the maximum. EVs is that energy which opposes the electron with maximum kinetic energy, isn't it? So potential difference depends. That stopping potential depends on what factor? It directly depends on the Emax. Emax depends on what factor? As we know, HF is equals to HF naught plus Emax. So Emax is actually HF minus HF naught. HF is what? H is Planck constant. F, it depends on incident electromagnetic wave, and F naught is depends on the material, the material of the metal plate. So these are the two factors on which the stopping potential depend. Okay, now suppose we keep constant the incident light. For example, it was 10 watt. 10 watt. Okay, but now it was 10 watt. Now what we will do is we will change it 10 to 20 watt. What does it mean? It means the number of photons that are incident on the metal surface will be increased, will be doubled. So the emitted electrons from this metal surface will be doubled. So on increasing the current, on increasing the electric field, the current will be doubled. So the graph then will look like it will be double. The saturation curve will be look like this, and if we extend the current axis, let me extend it, show how it will look like. It will look like this. And the stopping potential, as I told you, the stopping potential depends on what? It depends on the stopping potential depends on frequency of F, isn't it? Frequency of incident electromagnetic wave and material. Here, what we have changed? Here we have changed the intensity, that is the brightness of the incident light, not frequency. We have not changed the material. So the stopping potential should not be changed. Then how the graph will look like? It will be stopped only at that voltage. So the graph will look like this only. Okay. Now we want to do one more experiment. We will use 10 watt, 10 watt, 10 watt, but their color will be different. That is, their frequency will be different. Suppose we will use 10 watt blue light, 10 watt green light, and 10 watt red light. Okay, and this is the metal surface. The experimental setup is same. So I am not drawing the diagram again. I am just drawing the. I'm going to draw the. I'm going to draw the graph only. Okay, I'm going to draw the graph only. Okay, what will be the case? See, first of all, 10 watt, 10 watt, 10 watt. All of them are of equal wattage. So the waves, the waves are of equal intensity, so the equal amount of electrons are incident on the equal photons are incident on the metal surface, almost equal electrons will be emitted. So the saturation current due to all the lights will be same. The saturation current will be same for all of them. Then what will be the difference? You tell me. Let us here along x-axis we are plotting frequency. No, we are plotting what we are plotting, we are applied force, and in this direction current. Okay, so let us take first blue line. As we know, the stopping potential depends on what? The stopping potential depends on the incident electromagnetic frequency of incident electromagnetic wave, and the second is material. But here the material is same. Let me write, material is same. That is, the metal plate is same metal plate. Okay, metal plate is same. And what will happen? In this case, the stopping potential will be different. Stopping potential will be different. Let me write the equation once again. As we can see, whose stopping potential will be more? Stopping potential will be more for that frequency whose energy is maximum, isn't it? So in this case, whose energy is maximum? Energy will be maximum. Energy is increases when frequency is increases. If we write Vibgyor, then so in this direction the frequency increases. So the red one has the maximum frequency, that is maximum energy, then the green, and then the blue light. Where is the blue light? Okay, here is the blue light. So the energy of the blue light is maximum, Vibgyor. So here I have written little wrong, Vibgyor. Okay, so fine. Whose energy is much? Here the blue, then green, then red. So blue light. So we take the blue, it's it's it will be like something like this. Here is the stopping potential for blue. Then whose energy is green? Then the green. So current for green will be something like this. So stopping potential for green is this. Then for red, it has less energy, so it will look like something like this. That will be the stopping potential for the red. Okay, so stopping potential depends on the incident light as well as the material, and the saturation current depends on the saturation current depends on the intensity only. Okay, here the intensity was doubled 10 to 20, so that is why 10 to 20 the intensity, the saturation current was doubled. Okay, so I hope the photoelectric current is clear to you. Remember this photoelectric effect, the discovery or explanation of photoelectric effect gave Einstein Nobel Prize. Okay, see you in the. I hope you all understood this topic, and if you have any doubt, then do let me know through my profile in R1 Pro, and see you in the next class.